this and okay. All right. Okay, so last time we talked about a lot of confusing concepts and terms, right? I hope you can like you had chance to review the lecture notes and the book to make sure you can tell the difference between those terms. Yeah, very confusing, but it's important. So, okay, we talk about the definition for the genotypic value for three different genotypes, right? So suppose this is a F2 population. For any locus we could have three possible genotypes, and this is how we define the genotypic value for the three genotypes at this locus, if this locus is under the Hardy-Weinberg equilibrium, right? And if this is the case, we knew how to calculate the population mean, the expected genotypic value for this population, right? Just based on the formula. So the expected genotypic value for this locus in terms of these three genotypes will be the summation of each possible genotypic value multiplied by its probability. So we need to add up the three terms, then we can get this. So this is important. In the final exam, I could ask you to derive this equations for me, and also this. Okay, so if for the same locus, if I ask you to calculate the variance of the genotypic value in the population, all right, this is the definition, right? So you simply like calculate this and plug this values in this formula, then you can get the answer. Okay. All right. And we also talked about the average effect of allele, which is defined as the deviation from the population mean, right? So for allele A1, this is the average effect for A1. So try to understand why we use this formula to calculate this, and the same for the allele number 2, the A2. Okay. And the difference between these two allele effects will be defined as the allelic substitution, like this. All right, and we can easily rewrite the average effect for each allele, each of these two alleles, by using the allelic substitution term, right? Okay, and this table actually summarizes. Okay, so this slide first, we define a very important term in genetic breeding, which is the breeding value or breeding power here. So A11 and A12 and A22, right? And okay, so that's the expected value, right? That's the expected breeding genotypic value for this genotype, A1. The same, the breeding value for these two, for these three genotypes, and the observed genotypic value between this breeding value, the expectation, will be called the dominance deviation, and this part is actually the nonlinear part. So that's why the linear model, prediction model, cannot explain this part. So we call this part as the dominance deviation, yeah, for 3 genotypes. Okay, so this was what we learned the last time. Let's continue today. Okay, we talk about linear model and the least square. So we're gonna talk about we're gonna revisit this part today. Okay. Okay, so this slide actually shows the components of the genetic variation. So in genetics, in the breeding program, we are very interested in this term. This term is called the variance of the genotypic value in the population, right? In the previous slides, we have learned how we calculate this, and this is the results for this. And so as you can see here, so the total genotypic variation actually consists of 2 parts. So the first part is the variance due to the additive effect, and the second part, second component, actually represents the genotypic variation due to the dominance deviation, which is the nonlinear part. Okay, so why this is the case? So we can use this formula to prove this. So first, we can easily calculate the expected value for the breeding value in the population, right? So we just calculate the expectation for the breeding value, which is the additive parts, using the same formula. So that's the breeding value for this genotype, and using this probability, the same, right? And if you expand this equation, so you can easily find this equals to 0. And the same thing, so you use the same formula to calculate the variance for the breeding value for the whole population, which is defined using this. Why? Can anyone tell me why this is like this? Usually, like if we want to calculate a variance x, it will be expanded like this, right? Oops, x square minus expectation x, right? Yeah, this is the formula. But why this is like this? Because we have already calculated EA, the expectation of the breeding value, equals to 0. So this term equals to 0. So it's gone. So this part is gone. So we only have this, right? Okay. So that's why we got this. And if you just expand this using the same formula, the expectation, and you got this. So that's the variance for the additive parts for the breeding value for the whole population. Okay. And we follow the same strategy. Yeah. So we can also calculate the expected value for the dominance deviation, which is the nonlinear part. And the same, you can easily prove this is 0. And we use the same formula to calculate the variance of the dominance deviation, and this will equal to this. So if you add up these 2 parts, if you add up this parts and this parts, that is here, right? So you can, following this, you can prove that the total genotypic variation in the population at this locus consists, it is the sum of the variance due to the additive parts, breeding parts, and the variance due to the non-additive parts, the dominance deviation. So any questions here? Okay. So in the final exam, I could ask you why, for example, in a F2 population, if we consider any locus, for example, and this locus can take one of the 3 possible genotypes, right? And if we have the breeding values for these three genotypes. And we also have the dominance deviation for the three genotypes. And how do you prove so please prove the total genotypic variation is the sum of the variation due to the breeding part, the additive part, and the variance due to the nonlinear part, the dominance deviation. Just follow the slides and prove this, then you are done. Okay. Okay. And we also defined the heritability, right? So usually when you in the future, when you are involved any breeding project, either the animal breeding or plant breeding, sometimes you're gonna do the cultivar or animal selection based on some traits, some observable traits. And for each trait, there's a heritability. The heritability actually is defined as the proportion of the total phenotypic variation that can be explained by genetics, right? So that's why let's look at the broad sense heritability first. So this is the heritability, and so the heritability here, the broad sense heritability is a ratio. The denominator is actually what? Is actually the total phenotypic variation, right? Observed in the population. So the total phenotypic variation actually consists of the breeding variation, the variation due to the breeding value, the additive part, the non-additive parts, which is the dominance deviation, and the environmental parts. Okay. And so this actually, these three add up to the total variance observed in the phenotypes. So heritability actually is the proportion of this total phenotypic variation that can be explained by genetics. So out of the three components, these two components are due to the genetics, right? So this is genetics, additive genetic effects, but this is the non-linear genetic effects. Okay, so the sum of these two represented the variance due to the genetics. So this perfectly defined this term. The heritability is defined as the proportion of the total phenotypic variation that can be explained by genetics. Make sense? All right. So, but in reality, so when you are doing some breeding project, so it's very hard to calculate this. Why? We know, right? Because usually you use linear combination model to do the genomic selection. But it's very easy for us to handle this part, the breeding value part, because that is the additive part. But sometimes, like, it's quite difficult to handle this. For most of our genomic selection model, the prediction model, we can only predict this part. So that's why you see very often you're going to see the narrow sense heritability. The denominator is the same. That's the total phenotypic variation you observed in your study population, but the numerator just consists of this part, the breeding part. So, and we are interested. So here we just calculate what is the proportion of the total phenotypic variation can be explained by your model, by your linear model, by additive part, right? Additive genetic effect. Does that make sense? Any questions?
What would be the merit of having the narrow sense if it's not
narrow? Okay, because this is usually so when you try to, so for example, if you have a training population, right? That's the population you want to study, and and you want to develop a model from this training set, from this training population, you want to develop a linear prediction model. So suppose from this population, you got a model, and you want to apply this model to some other validation population or a breeding population, right? Okay, now the model, since the model is linear, it can only explain this part. This part we cannot, right? So that's why when you apply your model with this breeding population, you can only use this model to explain the additive part, the variation due to the additive part in this validation or breeding population. So that's why, so this is more accurate, but this is not that accurate. So that's why, that's the merit for us to use the narrow sense heritability. Because it can be repeatedly applicable once you define a linear model with this narrow sense heritability.
Mm-hmm.
Okay. Good question. Yeah. Okay. All right. So let's look at a F2 family, and suppose for each locus, the two alleles, the biallelic population is under the Hardy-Weinberg equilibrium. And if this is a F2, right, and it is a Hardy-Weinberg, then we can immediately know the allele frequency for these two alleles are equal to one half, right? And okay, if this is the case, we can use this allele frequency to calculate the genotypic frequency, right? This is for the A1, A2 heterozygous and homozygous A2, A2. So we can easily calculate the genotypic frequency, genotype frequency, all right? And so this is how we calculate the average effect of the allelic substitution, right? The difference between alpha-1 and alpha-2. Okay, and we have proved this. So the gene for the F2 population, the variance of the genotypic value for this population will be equal to this, right? And if you plug this allele frequency into this formula, you got this. Is that clear? Okay. And okay, now, so this is very important. In the future, when we try to use something like GWAS to scan the genome, in order to find the potential association between any underlying loci with the phenotype, we are going to use this model, right? So this is the model we're going to use. So that's the genotypic value. I'm sorry, that's the phenotypic value, right? Sorry, that's the phenotypic value. And this is the, what is this? Mu, the midpoint, right? Do you still remember? Yeah, yeah. Okay, that's the additive part, and that's the dominance part, right? Okay, for any locus, all right? And we use this random variable to represent the three genotypes that is associated with either the additive effects or the dominant effects. So I'm gonna move slowly here because this is very important. Okay. All right, this is how we set up a linear combination model to help us to do the computation by which we can find the association, the genotype and phenotype association. Okay, now let's look at the additive parts, because this is an F2 population, so we have three genotypes, right, for any locus. And so for A1, I hope you still remember, for this one, we have a positive additive. We have a additive effects, right, positive. So that's why we define a +1 for this genotype. Is that clear? Any questions here? So this is a linear combination model. For example, if this is a genotype of A1, then this, sorry, if this is the phenotypic value for A1, then this phenotypic value will consist of a midpoint, right? And you're gonna see a here, right, plus. So that's why we put a +1 here. And because this is a homozygous, so there's no dominance effect for this A1 genotype. Do you still remember? Do you agree? So that's why we define for this A1, the phenotypic value, we define W equals to 0 for this genotype. Make sense? Okay. All right, the same. So if we look at, if this is a heterozygous individual, and the phenotypic value actually consists of the mu as well, right? Mu is always there. But for this heterozygous individual, there's no additive effects. Do you still remember? So that's why we put a 0 here. But for this heterozygous genotype, there's a dominance effect. So that's why we define W, this random variable, as 1 in this case. Make sense? The same. Okay. For the G2, for this genotype, the for the A2, for this phenotypic value, this phenotypic value for this genotype actually consists the mu as well, the midpoint. But for the homozygous A2, we have a -a, right? Do you still remember? So that's why we define the Z as -1 in this case. Since this is a homozygous, so there's no dominance effects. Again, we're going to define it 0 for W. Okay, makes sense? Okay. All right. So this is how we define this 2 random variable. Okay, pay attention, please. So the Z random variable is associated with the additive effects, and the this random variable is associated with the dominance effect. And once we have this, we can easily prove this, right? So we know the genotypic variation is defined, is the sum of the variance due to the additive effects and the variance due to the dominance effect. And this is how we calculate the variance, right? And if you plug this in, then you immediately got this answer. In a F2 population, the variance of the phenotype equals to 1/2 multiplied by the additive effects squared plus the 1/4 the dominant effect squared. Okay, and this is how we prove this. And if you want to calculate this random variable, I assume everyone now is very comfortable to use the formula for calculating the variance for a random variable, right? So this is how we do this. Okay, so the variance of the Z variable here is actually this part and this part, right? And then we knew this part is like this. We have 3 genotypes, right? With the probability equals to 1/4, 1/2, and 1/4. And for the first genotype, the Z square equals to this, and this, right? And this part is the expectation part, equals to 0. We have proved this, right? So once you simplify this, you got 1/2. The same for this. So if we want to calculate the variance for the random variable W, so the same here. And you got this. And in this case, this 2 random variable, the Z variable and the W variable, Z is for the additive effects, and the W is for the dominance effects. And the covariance between this Z and the W equals to 0. So we're going to show you why this is true. So, okay. And I'm not going to spend too much time on this. This slide just show you how we calculate the variance for any random variable, right? And if we have two random variable, X and Y, so this is the formula for us to calculate the covariance between these two random variables. And we're going to use this formula to prove in our previous example, in F2 population, the two random variables Z and W, the covariance between them equals to 0. Okay. All right. So this slide is very important because I remember in previous quarters I gave this. In previous years, I gave my students a question like this. Suppose this is a F2 population, and suppose we define a linear model like that to describe the relationship between the phenotypic variation, the phenotypic value, and the additive and the dominance effect. Please calculate the variance of the Z variable. So this is how you need to do, right? So for a F2 population, and if the P1 equals to P2 equals to 1/2, the two allele frequency is equal to 0.5, then how do we calculate the variance of the Z random variable? So this is how we calculate this. Any questions here? So this is how we calculate the variance for the W random variable. Okay, and this is the part. So to show the covariance between Z and W. Right? So the covariance calculate, if we want to calculate the covariance between Z and W, so this is the formula. We need to calculate the expectation of the product of Z and W first, and then we need to calculate the expected value for Z multiplied by the expected value of W. So sorry, this is a typo. Once we have this, we can easily use the formula, right? So the product of Z and W, they can take like the three possible values with this probability, right? So we just use the formula to calculate this term. And we knew the expectation for Z equals to 0, and the expectation of W equals to 1/2, and the product of these two equals to 0. So, and if you calculate this term is also equal to 0. So, bingo, you can successfully prove the covariance between Z and W equals to 0. So this is how we show there's no correlation between these two random variable that we used for this linear combination model for this F2 population. Any questions? I'm gonna take a small break to answer any of your questions. And this part is important. I don't think I can write any like R code to practice this part, but basically you need to understand this, and I might give you some questions like that in the final exam to ask you to prove the covariance, the correlation between Z and W is equal to 0. Yeah, no correlation. Any questions here?
So this is just a property?
Yes.
Okay.
Yes, but this is only for the F2 population. So if and the two allele frequency are identical, right? This is a special case. That's why you can get this probability, right?
Yeah.
Otherwise, if it is still a F2 population, but if like, let's say the first allele, you got like 0.3, but the second allele, you got different proportion, the percentage, right? 7. Then you need to change these values right here, right? Yeah. So I will always give you a question for an easy situation, straightforward situation. I will not make the question super hard to. So yeah, but basically here I try to help everybody understand. So in this very specific situation, why if you define the linear model using this way, so why you can get this like correlation between Z and W equals to 0, right? They're not correlated with each other. All right. Any other questions here? Okay, very good. Okay, so I think I'm done with the chapter 5. And we're going to use a lot of information learned in chapter 5 and apply them to the following chapters. So now chapter 6 is the major gene detection. Major gene detection is something like the GWAS, because in a F2 population or some other breeding population, you can get the genotype at each locus, right? And so for the whole population, and or for a sample, big sample, and based on the sample, the data from the sample, you can easily test. You can use what we have learned to test if there's a significant association between this locus and the phenotype of interest. So this is the phenotype, let's say, phenotype. And so first, you can do the test to test whether this locus, the locus is associated with that. How do we do that? We use this model, right? The phenotypic value equals to what? Equals to the mu plus Z alpha. I hope you still remember this. We just defined this model, right? This is a very nice model. Trust me, very good model. And okay, so you can always use this model to describe the potential relationship between the phenotype and the genotype, right? This is the genotype, right? Okay, and we want to. So in this test, in this specific test, we have non-hypothesis, right? Non-hypothesis means like this is a neutral loci. It is not responsible or contributing to the variation in the observed phenotype. So which means the non-hypothesis is always like this. The additive effects equals to 0 at this locus, right? Or the dominance effects equals to 0 at this locus. Do you agree with me? Yeah. Okay, then the alternative hypothesis is what? So if your data does not support your non-hypothesis, you're going to reject the non-hypothesis. And the alternative hypothesis means like either the additive effects at this locus is not equal to 0, or the dominance effects is not equal to 0. So don't be confused here. So here the dominance effect is still additive part, not the dominance deviation. The dominance deviation is the non-additive or non-linear part that cannot be explained by this linear model. But here I'm talking about two effects, genetic effects at this locus, additive effects and the dominance effect. Both effects are additive, linear effects. Okay, don't be confused by this additive dominance effects with the dominance deviation. So those are two different concepts. Is that clear?
Sorry, I'm a little bit confused. So are we testing both these nulls at the same time, or are you just saying that we can have our nulls set to A equals 0 or D equals 0?
So that's a good question. We can test them simultaneously, or we can test them separately. Yeah, you can do either way. So for simplicity, yeah, just put them together. So you can test them simultaneously. So which means like usually we have a single null hypothesis, which means this locus is irrelevant to the phenotype, right? But you can have like different version of your alternative. So this is a little bit advanced. So you can have like an alternative one is like this. You can have a alternative one, two. It's like this here. A is not equal to 0, but D is 0. Or you can have another alternative version. So A equals to 0. But the dominance effect is not equal to 0. All right. So this means like, if you cannot reject your null hypothesis, which means like when you scan the genome, you're going to ignore this part because this locus is actually irrelevant with your phenotype, right? But when you scan the genome, if you identify any locus with either additive effects or dominant effects, or both, those loci are of your interest. So by doing GWAS, you hope to identify those multiple loci that are jointly contributing to your phenotype. Does that make sense?
Yeah, that makes sense. I guess I'm just kind of drive the point clear here. What if only D was greater than 0, then we would still say that we reject the null, right?
Right.
Okay. Yeah. I just want to make sure. I just want to make sure that was clear. Thank you.
Sure. No problem. Yeah. We're gonna talk about some talk about this again using some real examples to show. So only in this situation, only if you cannot reject this, that means this loci is a neutral loci. You don't worry about this. But if you see any effect, either A or D or both, is non-zero, is significantly different from 0, then that's a evidence or indication of association between this locus and the phenotype. All right, so in this chapter, we're going to talk about how we can use the test we have learned in the past to do the major gene detection. So in physics, sometimes like let's talk about the signal detection. So if in physics we want to test some real signal, and if we want to pick up a real signal from the background noise, so this is what we do, right? I'm sorry, this one. This is what we do here. Okay, so basically, suppose there's a real signal coming from the source, but if there's some like background noise, so what you receive from the receiver, what you can see from your a machine or monitor will be the combination of these two, right? You're gonna see the noise like this, plus this real signal. So, okay, based on this, you need to pick up this signal out of this noise. This is what the physics people they're worried about. So they use this kind of like statistic to help them identify the real signal. All right. So so in physics, sometimes you see this ratio is called the signal noise ratio. They compare the detected signal with the background noise. If this signal is, if the magnitude of the signal is comparable, is almost the same with the noise, which means like there's no signal. On the other hand, if the signal is significantly greater than the background noise, then they can claim this might be a real signal, right? So that's the signal noise ratio, which is commonly used in physics. In statistics, the same. We use the same concept actually. So we define a statistic to help us identify the real signal or real genotype-phenotype association in a GWAS. So we use the same ratio, but here the ratio is a little bit different, very similar to this ratio. So here the signal is becomes the estimated statistic based on your data. So this is the estimated statistic, and we compare your signal, the estimated statistic, with the standard error of this estimation. We're doing the same thing. If your estimated statistic is significantly greater than the standard error of this estimation, then we believe this is a significant results or a significant association. In this case, we're gonna reject the null hypothesis, which means there's no association, right? If your estimated statistic is very close to the standard error, then we don't believe this thing is a significant signal. Then we're gonna accept the null hypothesis. And in this case, this locus is irrelevant to the phenotype. Is that clear? Okay, right.
Just real quick, so your null hypothesis would be set to be that there is no signal.
So let me write this down. Yeah, it's confusing here. So the null hypothesis means like, let's just use the additive effect. We're doing the test, right? We want to test if this locus in F2 population, if this locus is responsible for the phenotype. The null hypothesis is like at this locus, the A equals to 0. There's no association, right? No additive effects. The alternative hypothesis will be A is not equal to 0, which means there is a association between the genotype and the phenotype at this locus. So this is the test, right? Okay, now using this test, we can estimate this A. So this is the A estimated from, so this is the additive effects estimated from your data. You collect your data, right, from this F2 population. And you can divide this with the standard error of the A estimation, all right? Think about the T statistic, t-test. This is the same with the t-test. All right, we can actually define this as a t-statistic. This is how we define a t-statistic. Okay, now, if this ratio is very close to 0, which means so let me think. All right, so if this t-statistic is very close to 0, which means this thing is very close to 0. Do you agree?
Yeah,
And then this is a indication. So if this is the case, if your t-statistic is close to 0, in another way, put it another way, is that the estimated additive effects is close to 0. This will be evidence in favor of this, right? In this case, you're going to get a very large p-value. Does that make sense? And you're going to accept the null hypothesis, which means, oh no, this locus is not a this locus is not a locus that is contributing to the phenotypic variation. We're going to pass this one. We're going to keep scanning the genome to find the real signal, right? What is the real signal? So when you scan the genome, so you're gonna find a lot of loci just like this, with the p-value great with the large p-value, but the t-statistic is close to 0, until you find something like really interesting here. Oops, you got a loci here, and this loci gives you what? Gives you a t-statistic which is significantly greater than 0. Let's say in this case, we got 100. Give me a second. The car is. It's okay. All right. And all right. So if in this at this locus, oh yeah, sorry, give me a second. I need to take care of my. I'm so sorry. The alarm went off. I just turned it off. Sorry. All right. So when we get this point, and if for this one we do the same, we perform the same test, and if this time you got a very large t-value like 100, then this result will be in favor of this alternative hypothesis. Is that correct? And this will shows, okay, this locus is likely contributing to the variability of the phenotype. Does that make sense?
That makes more sense.
Mm-hmm. Okay. All right. Any other questions here? All right. We're gonna do the same thing. We're gonna do. We're gonna repeatedly use the test we have learned to test each locus along the genome, and hopefully we can identify the responsible loci for the phenotype of interest. Okay. All right, let's look at the simple design, the backcross design. All right, this is the backcross design, right? So for backcross design, we only have 2 genotypes here. Oops. Okay, oops. Can you see my screen? Sorry.
We can see it, yeah.
Oh, okay. So I had some problem. It shows like I did, my sharing is paused. So, okay. All right, let's continue. All right, this is a backcross design, and for backcross design, we only have like two genotypes, right? Either this one or this one. Okay. So, okay, from now on, we're gonna use the linear model a lot. So that's why it's very important for us to understand this linear model. Okay, here in a backcross design. So for each locus, we only have 2 possible genotypes, right? Any questions here? This is the backcross design. So we only see 2 genotypes. We're missing one. So this is why this design is not as good as is not as powerful as the F2, because in F2 we can see all 3 genotypes, but for backcross we only see 2 of them. Okay. And this is how we define the association between the phenotype and the genotype using this linear model. What's the difference here? So when you compare this model with the model I just showed you in the previous slides, what's the difference? Can anyone tell me?
Z variable?
Say that again. I'm sorry, Mariano.
The Z variable?
Yes, the Z variable. Actually, I use X to replace Z. But what else? What else?
The W.
Yeah, W. Yeah, there's a missing W, right? Yeah, because the model I just showed you, that's for the F2, right? But here, this is a backcross. Backcross, we don't use W. Why? Because let's look at here. Because this is how we define the midpoint additive effects and the dominant effects, right? In the past, and we know the midpoint is the average of these two phenotypes, right? And the additive effect is actually the difference between the first phenotype and the midpoint, and dominance is the heterozygous, the difference between the heterozygous phenotype with the midpoint. Okay, so in statistics or in math, if we have like 3 unknown parameters, we need 3 independent equations to solve this, right? Otherwise, it's impossible. So that's the common thing. However, as I just mentioned, in the backcross design, we only observed two genotypes, right? So we observed this one, we observed this one, this one, this one, and this one, but we're missing this one. Make sense? So which means like we no longer have like 3 independent equations. So if we want to use 2 equations to estimate 3 parameters, that's impossible, right? You cannot get the unique solution for these 3. So that's why we have to sacrifice one. So we assume there's no dominance effect in this situation. Actually, there is, but based on this backcross design, the missing information, you cannot estimate that D effect. So and this actually the D effect is absorbed in the estimation of these 2 parameters, will be confounded. So I believe you have heard this kind of like concepts, right? If something is confounded, so you can never get the unique solution for some parameters here. So this is why for backcross design, we have to assume the dominance effect equals to 0. And in this case, we're going to use this simplified model, linear model, to describe the relationship between the phenotype and the genotype. So yeah, as Mariano mentioned, so this is the X variable. Actually, the X variable here is equivalent to the Z variable we used in the previous slide. And we use 1 and 0 to code this genotype and this genotype, or you sometimes you often see other coding. So you can define this X variable equals to 1 for genotype A1, and you use minus to denote the X variable for the heterozygous genotypes. Either way, this doesn't matter, because in statistics or mathematics, you can arbitrarily define your design matrix or the predictor variable. This will affect the scale of the parameter which you want to estimate, right? Okay. Any questions here? Is that clear? So for backcross design, we use a simplified model for testing. So I hope I make it clear here. The reason why we want to set up this linear model is to try to test whether this effect, additive effect, is real or not, right? So by doing this, we can scan the genome we can test each locus on the genome and identify the QTL. QTL means the quantitative traits loci that are responsible for the trait for the phenotypic variation. Okay. So this is how we use the least square to find the linear regression. So this is I hope you would agree, right? This is a linear model. So we try to translate this biological problem into a mathematical or statistical model. So we use this. We take advantage of using this linear model to help us to test the association between the phenotype and the genotype, right? And now, since we have a mathematical or statistical problem, we can easily use the mathematical way, the least square, to help us to estimate what? Estimate the B here. So this here, B1 is what? B1 is the A, additive effects, right? In our model. Any questions here? So I use different notation. This is the statistical way. So the B0 means the intercept and the B1 means the slope, right? But in our models, we use a slightly different notation here. So the B0 is the midpoint, right? The intercept. And the A here, additive effects, represent the B1, the slope. So we actually are testing the slope to test the association, to test the potential genotype-phenotype association. Okay, very good. All right, I'm going to show you some practice code. Let me see. I put some like sorry, give me a second. Where's my window? Your model. I cannot find my R window. Oh yeah, okay, it's here. So can you see my window? R window?
Okay. Yeah, we can see it.
Yeah, perfect. All right. So this is the practice code I posted on the canvas. And so here, I just try to simulate some data sets. So here, suppose we're talking about F2 design, and X1 means the Z variable. So let's say I generate the genotype for three for 30, sorry, I generated a sample of 30 individuals, and the X1 means some like binary like random variable 0 or 1, and X2 is another continuous random variable. So this is not exactly like the F2, but I just give you an example here. So I generated X1, which is equivalent, something like the Z variable, and X2 is something like the W variable. And I set up these three parameters here. So the intercept equals to 8. The additive regression coefficient equals to 2, the effects, and the second effect, let's say the dominance effect, equals to -2. And I can generate this data sets. So you can easily plot any two random variables here. So if you plot the Y versus X1, you're going to see a slightly different association, right? So the value, the X1 value generally have higher expression, higher Y value than those with the X1 variable equals to 0. So if you test a correlation, yeah, there's a correlation. There's a weak correlation between them, and so on. So in the linear model, you can run this to test whether these two effects are significant or not. So the X1 means the B1 effect. Here, the probability is close to 0.05, which means there's a weak association between the X1 variable and the Y response variable. And the same, when we tested the second random variable, second effect, the p-value is less than 0.05, which means there's a strong, significant association between the B2 effect and the Y response variable. All right, so I just mentioned this a little bit, so you can take time to run this code and try to link this code with what we have learned in the class. Okay, let's continue our lecture. Okay. So here, we actually translate our biological question into this statistic question. So by using this linear model, and we are interested in testing whether this slope either representing the additive effects, or it can also represent the dominant effect. So we want to test if any of these slopes is not equal to 0, and the non-zero, non-trivial genetic effects or non-trivial slope will indicate an association between the genotype, between this locus and the phenotype. All right, this is the kernel of the GWAS. This is the kernel of the association study. So how we can identify the trace associated loci by analyzing the high throughput genomic data. So something like this. All right. Okay. All right. The least square. Okay, we're still talking about the background design. Okay. So sometimes I just use different notation. I hope I didn't bring a lot of confusion in this. So this is the linear regression model we use for a backcross design, right? So that's why we only see two parameters here. So the B0 means the intercept, which is the mu here, and the B1 is the slope. And here we use B1 in the place of the additive effects. So the same, if you look at this equation to this equation, they're the same, right? We have two parameters here to estimate. All right. And by least square estimation or the maximum likelihood estimation, so this is how we calculate the slope estimation. We can use the data to estimate this parameter. Any questions here? And this is the equation we're going to use to calculate the intercept once we calculated the slope. All right, those are kind of like very basic statistical theorem. So I assume like you have already learned some of this in your statistics class. If not, please spend a little bit of time after class and Google and search for the least square or linear model estimation. And those Google page, Wikipedia page will give you a lot of like useful information to help you understand these equations for estimating the parameters, the slope, and the intercept for a simple linear regression. Okay, so we use a very, very simple linear regression for the backcross design, right? And this is how we estimate the residual variance, which is normally distributed. And we need to use this to calculate the estimation of this, the standard error of the estimation of the slope, right? I hope you still remember. So in statistics, we try to construct a ratio, a test statistic. The numerator is the estimated slope, and the denominator is the standard error of the estimation of this parameter, the slope. And the reason why we want to calculate the residual variance is because we want to use this to calculate the standard error of the estimation of the slope. Once we have this and this, we can easily construct a ratio of this to form a tested statistic, either chi-square or f-test or t-test, to help us make a conclusion. So any questions here? Okay, very good. Okay, so in this simple linear regression, we have two parameters, right? We need to estimate two parameters. One is the intercept and the other one is the slope. So if we translate back to our biological language, so we want to estimate the midpoint and the additive effects in the backcross design. And in statistics, so when you try to construct a test or calculate the residual error variance, you need to use this term, the degree of freedom. The degree of freedom, so also, if you are not very familiar with this term, so please Google and try to find a Wikipedia page for this definition. So basically, the degree of freedom is equal to the data points. So this is your sample size. Suppose you have like 30 samples in your backcross design. So this n equals to 30. So initially you have 30 degree of freedom. However, if you try to set up a linear regression model like this for the testing, so the cost of using this model, linear combination model, is 2, because you have to use your data to estimate 2 parameters, right? The cost of using this linear, so nothing is free. So when you try to use something, you have to pay for that, right? The cost for using this linear combination model is 2, because you have to use your data to estimate these 2 parameters. That's why you see for this problem, the degree of freedom equals to n minus 2 equals to 28. So you used up 2 degree of freedom to estimate these 2 parameters, such that you can use this linear combination model to help answer your question. Does that make sense? Okay. All right. Okay, the backcross design. So now we're still back to our linear regression model, right? And we are very familiar with this now. So I assume everybody will be expert now, right? So here we actually want to test whether the additive effects equals to 0 or not. The slope equals to 0 or not. And this is how we estimate these 2 parameters, right? And the variance. And we can, so once we have the estimation for this slope and the variance of this slope, of this estimation, so this is what we can do. We can use the F statistic. We construct a ratio. See, we got this ratio again, right? This ratio looks very similar to the ratio I just showed you, the signal versus noise ratio. So the numerator is actually the signal. The signal means like the estimated slope or the estimated additive effects from your backcross design data. And the denominator is something like the background noise. So we want to estimate the variance of this estimation. The ratio of these 2 actually the ratio of these two things develops a F statistic. And this statistic is following a F distribution with the degree of freedom equals to 1 and n-2. So the n-2 is equal to the total degree of freedom of the data. So I just explained why we have the n-2, right? And this one means you only tested this single parameters here. So I'm going to answer Adrian's question. So sometimes if we want to test, so this is a backcross design. So we only want to test a single effects. But for a F2 design, we may want to test additive effects and the dominant effect together, right? We want to test these two simultaneously. Then we can construct a F test with the degree of freedom equals to 2 and n-3. Why n-3? Can anyone tell me why n-3 rather than n-2 here?
It's because you're testing the additive effect, and then the dominant effect, and then the actual the average.
Yes. So actually, right. The 2 here means like we want to test the 2 effects, right? Additive and dominance. But why n-3? Because for the F2, we do not use this simplified model, right? We're going to use a y equals to mu plus xj or zj. Let's use zj additive plus wd, right? Plus error term. Okay, how many parameters are involved in this new model? We have 1, which is B0, the intercept, right? We have 2, B1 is the additive, and we have B2 for the dominance. So here we need to estimate 1, 2, and 3 parameters. That's why we need to -3, because the cost of using this linear regression model is 3 degree of freedom. Does that make sense?
Yeah, that makes sense.
Okay. So by doing this, so I hope I can tell you a little bit information about the difference between using this model and this model, because these are 2 models, right? The simplified model is for the backcross design, because in backcross design, because of the missing data, we only need to estimate 1 parameters. But with the F2, which is the full data, the complete data, so we can use the full model. And in this case, we need to estimate 1 more parameters. That's why you're going to lose 1 more degree of freedoms here, right? Oops. Okay, very good. And I hope you can see this. So this is very similar to this ratio, right? We always do something like this. So we do something like the signal versus noise ratio to help us detect the signal, the association between genotype and the phenotype. Okay, so this is the F table, the distribution table, and the same. So since we know how to use the chi-square, this is the same. If we just test 1 parameter, the slope for the backcross, we just look at the degree of freedom equals to 1, right? This column, and this column gives you a different degree of freedom of the second. Give you this y-axis actually give you the different degree of freedom, the second degree of freedom. This is associated with the sample size. The sample size -2 equals to this. So suppose you have 30 individuals in your backcross design, you need to look at here, right? So this is the critical value you need to use to calculate your p-value. So if you have a very large sample size, let's say 100 or 1,000, then this degree of freedom will go to infinity on this axis, right? On this y-axis. All right, then this value is very close to, do you still remember this value? This value is the cutoff value, the critical value for the chi-square distribution. The p-value is associated with the 0.05 with the degree of freedom equals to 1, right? Which means the second degree of freedom, when your sample size is going to the infinity, this F distribution is very close, is getting very close to the chi-square distribution with the degree of freedom equals to 1. All right. Okay, very good. And so this is some information I took from the Wikipedia page showing the property for the F distribution or the chi-square and the relationship between the chi-square distribution and the F distribution. All right, so I'm going to stop here because next time we're going to continue talking about the F2 design. So as I mentioned, because the F2 in the F2 design, we can observe four information. We have the information for all three genotypes at any locus. So which means we have like 3 equations to, and we will be able to estimate all 3 parameters here. Then we're going to use a full model. So in this model, we have another term here, right? We use this to estimate the dominance effect. Then with the F2 design, we can test both effects to see if any of them is non-zero. Okay, so I'm gonna stop here today. And any questions for today? Oops, sorry. Okay, very good. So I'm gonna keep making some like practice code, and try to. So when you practice those R code, you can think about you can try to associate those code with the stuff we learned in the lecture, and basically I'm gonna give you. Thank you. Basically, I'm gonna give you a very simple and straightforward situation. But you can, in the future, you can easily expand this knowledge to handle like more complicated situation. In the future, when you do your research, if you have like questions, yeah, we can meet and discuss, and we can try to apply some of our knowledge learned in this class to solve your problem, yeah, in your research. All right. Thank you, everyone. Sure, my pleasure. See you next time.
Bye.
Bye.